Welcome, ladies and gentlemen, to this course on emission-oriented transportation management. My name is Prof. Meisel. I'm Professor for Supply Chain Management at Kiel University in Germany. I'm interested in green logistics and I want to share some of the concepts from this field with you in this course. I hope it's interesting for you and you learn something. Good luck. On the first slide, you see a list of elements of a logistics system that cause emissions. First of all, we have the transport services themselves. If a vehicle goes from location A to a location B and uses fossil fuels, these fossil fuels are burned and the corresponding transport service is responsible for the emissions caused from burning these fossil fuels. We also have handling operations and inventory holding, warehousing in logistics, and these activities are also associated with emissions. Administration as well as the production, maintenance and the disposal of vehicles cause emissions too. The latter calls for a life cycle assessment of logistics assets. In the lower part of the slide, we see an example of such a life cycle assessment for a Panamax tanker vessel. The table shows us shipbuilding, the operation, maintenance of the ship, and finally dismantling at the end of the lifetime. We see a number of types of emissions: carbon dioxide, carbon monoxide, CH4, NOx, and so on. And from this table we see that these emissions are caused to different extent throughout the four life cycle stages. Carbon dioxide is almost completely emitted while operating the ship. 96% of all carbon dioxide emissions result from running a ship from one port to the other. For other types of emissions like CH4, we get a different picture. About 80% of CH4 are caused when building the ship, but just 11% while operating the ship. This means that in different stages of the life cycle of logistics asset, we have different types of emissions to a different extent. In what follows, we focus on the operations, the transport services, and the emissions that result from running these vehicles. At the second slide, we have another important aspect that has to be taken into account when assessing emissions of vehicle operations. This is the so-called well-to-wheel assessment, and it takes into account that emissions basically result from two things. First one is the emissions that are caused while the vehicle is running. It burns the fossil fuels and the exhaust consists of negative emissions that we actually want to avoid. But there is also another type of emissions, and these are so-called well-to-tank emissions, which result from the production and distribution of the fuel itself, including the mining of raw oil, the transportation, the refinement of such an energy carrier, and the transportation throughout the whole fuel supply chain towards the vehicle. You could say well-to-tank emissions are those emissions that result from all activities before the fuel is actually available at the gas station. Of course, for an objective assessment of logistics operations, we have to take both into account tank-to-wheel emissions, TTW, and well-to-tank emissions, WTT, which sum up to well-to-wheel emissions, WTW. At the third slide, you see so-called emission coefficients of various types of fuels and electricity. This is relevant because we have different types of vehicles using different fuels. We might even have electric vehicles that use electricity. And these different fuels and types of electricity come along with different emissions per liter of fuel or kilowatt hour of electricity. At the top of this list, you see diesel. Diesel causes well-to-tank emissions of 0.57 kilogram carbon dioxide per liter. Tank-to-wheel emissions of 2.67 kilogram carbon dioxide per liter. which sums up to well-to-wheel emissions of 3.24 kg carbon dioxide per liter. You will see that the unit of measurement is not just carbon dioxide per liter, it's carbon dioxide with a lowercase e per liter. This E stands for equivalent and is read as carbon dioxide equivalence. What does this mean? It means that burning a liter of diesel not just emits carbon dioxide, but also other types of greenhouse gases. In order to jointly account for these different types of greenhouse gases, we can bring them together as so-called carbon dioxide equivalents that reflects the individual global warming potential of these different types of emissions and breaks them down to similar values of carbon dioxide. This helps us to compare the environmental impact of different types of fuel. You see that other types of fuel lead to other well-to-wheel emissions. Marine diesel oil, for example, has well-to-wheel emissions of 3.53 kg carbon dioxide equivalent per liter. And for electricity, it very much depends on how you produce the electricity. If you use coal power, we have well-to-wheel emissions of 1.85 kg of carbon dioxide equivalent per kilowatt hour. If you use green power at the example of Germany, we have well-to-wheel emissions of 0.29 kg carbon dioxide equivalent per kilowatt hour. Note that for the electricities, we do not have tank-to-wheel emissions because operating the vehicle itself is clean. The emissions result at the stage of the production of the electricity, which is accounted for by the well-to-tank emission rate. On slide 4, we now approach the calculation of emissions from operating a vehicle. Let us assume that this vehicle already conducted a transport from sim location A to sim location B. In such a case, we can just measure the amount of fuel that was consumed by the vehicle. Let's call this quantity of fuel F. The resulting emissions are then simply computed by multiplying the fuel consumption F and the corresponding emission coefficient K that is taken from the previous slide and corresponds to the particular type of fuel that was used by this vehicle. Accordingly, for an electric vehicle that consumed W kilowatt hours of energy while going from location A to location B, the emissions are simply computed by multiplying the energy consumption W by the corresponding emission coefficient K, and here the emission coefficient reflects the type of power as we've seen at the previous slide. This approach can be applied on any scale, be it for an individual transportation process, for all transports that took place within a year, for all transports that were conducted by a company fleet, and so on. At the bottom of this slide, we see an example of land-based transportation, but the approach could be similarly applied to maritime transportation. The text of this example reads as follows. A large shipment of 14 truckloads can be transported from Munich to Berlin by a single trip of an electric train or by trucks. The train consumes around 4,600 kilowatt hours of mixed power. Each truck consumes about 216 liters of diesel D7 for going from Munich to Berlin. Empty traveling of all vehicles is ignored for reasons of simplicity. Question is, how large is the well-to-wheel emission of the two transport options? For the train, we simply multiply the 4,600 kilowatt hours by 0.62 kilogram of carbon dioxide equivalents per kilowatt hour, which results in approximately 3 tons of carbon dioxide equivalent. Note that the coefficient 0.62 is the well-to-wheel emission of mixed power for our example in Germany. For the trucks, we have 14 trucks, each of them consuming 216 liters of diesel, and the well-to-wheel emission coefficient for this type of diesel is 3.15. Multiplying 14 by 216 by 3.15 results in 9,525 kg carbon dioxide equivalent. This example shows you how to very roughly estimate the emissions that result from a transport process. On slide 5, we go one step further. Let's assume the transport services have not been conducted yet and we do not actually know how much fuel or electricity was consumed therefore. In this case, also the fuel consumption needs to be estimated. A very rough estimation could be as follows. Given an average fuel consumption rate E, measured in liters per kilometer of the used vehicle, a projected transport distance D of the transport process that we are looking at, and a well-to-wheel emission coefficient K that expresses the amount of carbon dioxide equivalents per liter of fuel. The emissions resulting from such a process would then be calculated from multiplying the fuel consumption rate E by the projected transport distance and the well-to-wheel emission coefficient. Of course, this fuel consumption rate E is highly specific on various properties of the transport process. What type of vehicle do we use? What is the type of cargo? How heavy is it? Is the vehicle almost empty or is it almost fully loaded? What is the road profile? Is it uphills? Is it downhills? Is it in flat terrain? And so on. For this reason, coming up with an appropriate value for E is not trivial. There exists various complex yet realistic emission estimation models that take these factors into account and try to compute E. For the sake of simplicity, we do not go into details with such more complex models. This ends the first part of this lecture. A list of references is shown here at the final slide. Feel free to use this material to think about further issues related to transportation and the environment. Some ideas are shown here at the bottom of slide 6. For example, what do you think? What factors actually affect fuel consumption in road, rail, and maritime transportation? Are these transport modes identical or do they differ in one or the other aspect? Or use the formula from the previous slide to estimate one of your own trip's emissions. For example, when you went on a vacation by car with your family. You could also try to estimate what the environmental impact is of running a diesel car over 100 kilometers or a petrol-driven car that uses petrol E10 for doing the same kind of trip.